We're going to start our discussion of patterns in the Android and Java concurrency frameworks by describing the monitor object pattern. And we'll start off first by explaining what the monitor object pattern does and what its intent is and its structure and its functionality and its participants and so on. And then we're going to go ahead and talk about how it's applied in Android and in Java. So to make this more concrete, we're going to talk about a particular use case. We're going to talk about implementing a blocking queue. And as you'll see, this is very common in concurrent programs. We've seen this over and over again when we talked about various elements in Java. It also occurs a lot in Android. So it's often the case that concurrent applications, concurrent services need to coordinate their interactions between producer and consumer threads. And a common way to do this is by having a shared queue, a shared blocking queue. So here's kind of a big picture of this. You can see that we've got a producer thread that's going to put things into the shared queue as long as the queue isn't full. And we have another thread, a consumer thread, that's going to take things out of the queue, the shared queue, as long as the queue is not empty. Now, what's the problem? Well, we've talked about this earlier, but to recap, if you do a naive implementation of a blocking queue, you'll have race conditions, or you'll have busy waiting when multiple threads attempt to put and take items into or from this shared queue. So if you don't have any synchronization, if you just have a good old, Java array list or Java linked list or something that lacks synchronization altogether, then you're going to end up with lots of corruption because the internal state of the queue will be munged and corrupted by having multiple threads trying to update and access its fields simultaneously for all the reasons we've talked about over and over again. Bad news, race conditions galore. Likewise, if you do something very simple-minded, like just use a synchronized block, then you can end up with busy waiting, because when the queue is empty, it won't corrupt the state, but it'll just return right away, and you'll have to write a busy loop or a busy wait that sits there and just neurotically checks over and over again to see if the queue is empty or full. So what's a better way to go? Well, a much better way to go here is to apply the monitor object pattern in order to synchronize a shared queue efficiently and conveniently. And so as you can see here, we're going to have a queue that's implemented using a monitor object, and it's going to have its methods be synchronized. They may not necessarily be synchronized in the sense of the Java synchronized keyword, but the effect will be that they're synchronized in that only one call to a method on a given shared queue object can be running in the context of that shared queue object at a time. And to make this work, we're going to have a couple of things, because this particular implementation is going to be really optimized, and it's going to have two monitor locks, two reentrant locks, one for handling putting into the queue and the other handling taking from the queue. And then we're also going to have a pair of monitor conditions. And these monitor conditions, of course, are going to be used to allow us to differentiate between the state where the queue is empty, where we want to wait for it to be non-empty, and also the state where the queue is full and we want to wait for it to be not full. So if you go back and watch the earlier stuff we talked about for monitor objects, you'll see that that's very hard to implement, or very inefficient to implement, using built-in Java monitor objects. So of course, we're going to do it with reentrant locks and condition objects. And just to make this even more interesting, we're going to show the implementation of the linked blocking queue, which is actually some code you can get right out of the Java util concurrent package. And in fact, of course, since Android has these capabilities as part of it, then you can also use this in Android too, because it supports this. So we're going to take a look at using monitor object to implement a blocking queue. And as you'll see here, because we're going to do this in a super efficient way, we're going to have reentrant lock. There'll be two instances of that. We're going to have two condition objects. And as you can see here, I've kind of used notation to indicate how the various elements in this implementation map back to the monitor object pattern. So the linked blocking queue is the monitor object. The reentrant lock is the monitor lock, or monitor locks, as the case may be in this situation. The condition objects are monitor conditions. And then we have a client, and we have a client that will be putting things into the queue and a client that'll be taking things out of the queue. And the cool part about this is you could use this in Android to have the user interface thread accessing stuff from a queue. And if it was carefully designed, you could have it block for just a short amount of time, for example, with timeouts, so it wouldn't wait too long. So we're going to use the monitor object pattern in order to do this. And you can see that there's a couple of different ways to do it in Java. One is to do it with linked blocking queue. The other is to do it with array blocking queue. We're going to talk here about linked blocking queue. The main difference between linked blocking queue and array blocking queue is that linked blocking queue is more cleverly implemented by having a pair of locks, so that adding things to the front or taking things off the front or adding things to the end will be more efficient, because the locks will be segregated. There will not be a single lock, so therefore you won't have to worry about as much contention. So before we get into the implementation details, however, let's first take a step back and take a look at the monitor object pattern as it appears in the classic POSA 2 book. This was actually published about 20 years ago, and this was a culmination of about a decade's worth of research I've been doing as both a graduate student and a professor at Washington University. So I documented this pattern, and then it appeared in the book. So the intent of this pattern is to synchronize concurrent method execution to ensure only one method at a time runs within a given object. And the other part of the intent is to allow the object's methods to cooperatively schedule their execution sequences. And we'll see how that's used with the condition objects to allow a thread to wait, or threads to wait when the queue is not empty, and as well as to allow a thread or threads to wait when the queue is until the queue is not full. So let's talk about when you actually want to apply this pattern. So one applicability is when an object's interface methods are a natural way to define its synchronization boundaries. That's not always the case, but it's often the case. And it really helps to make things more intuitive when that is the case, because it's easy to reason about a concurrent object where you have the methods be the synchronization points. So for example, taking and putting in a shared queue, that makes it easy to reason about. And this in some ways is just an extension of the traditional classic object-oriented programming model. We know how to make method calls, we know how to put objects together, and we know how to invoke methods on objects, and now we just do it in multiple threads, and the method calls are what coordinates and synchronizes. You should also apply this pattern when only one method at a time should be active within an object. And of course, the whole point of that is to ensure that we can essentially maintain and manage critical sections. So you do this, you want only one method at a time so that you can ensure that mutable shared state is not corrupted by having multiple methods inside the object making changes that are not coordinated. And then we also want to do this when the objects should be responsible for transparent method serialization. You make the method calls in whatever order you feel is, or whatever order you do, and then the object is responsible for making sure things run in the right order. For example, you don't allow a method to run to take something from the queue if the queue is empty, right? That's something that the object can coordinate on your behalf. We do this because we really don't want application developers to have to reason about these low-level mechanisms like reentrant locks and condition objects. We just want them to make method calls and have the magic of the concurrency environment, the pattern-oriented implementation of whatever uses this pattern to shield the application developers from all these low-level niggling details. And then another property you want to have here is you want an object's methods to be able to interact cooperatively by coordinating the order in which they run. And again, it's kind of, you make a method call to take something, the queue is empty, you wait, right? And some other thread gets a chance to run to put something into the queue. And one of the things we'll talk about when we get into the implementation details is that we're going to have to make sure that locks are properly used to ensure that object-specific invariants hold as the threads suspend and resume their execution. So when a thread is held, then you don't have to worry about the invariants because nobody else can get in there and discover that things aren't quite consistent. But when the locks are released, then the invariants have to hold, because otherwise chaos and insanity will break out. So let's talk about the structure of the monitor object pattern as it's described in the POSIT 2 book. So here's what the pattern looks like. If you take a look at the book, you'll see a diagram that looks sort of like this, probably not quite as colorful because the book's printed in black and white, but this is the basic idea. So here's the monitor object, and you can see we have a monitor object with a bunch of synchronized methods, and then we've got one or more monitor conditions and one or more monitor locks. And there's a containment relationship between the monitor object and the monitor locks and the monitor conditions. And then one or more clients can access this thing. So the monitor object is where the methods are defined. Pretty straightforward. That would be something like the put and take methods on the linked blocking queue. And then we have monitor lock, and that has methods for acquiring and releasing the lock. And that would be things like the Java reentrant lock that's used for the take lock and the put lock, which are part of the underlying implementation of the linked blocking queue. And then finally, we have monitor conditions, which in our case are the Java condition objects that are used for the not empty and not full conditions that the monitor object, or the linked blocking queue in this case, use in order to be able to implement the semantics of a blocking queue. So with that knowledge of the structure of the pattern, let's now take a look at the dynamics of how this pattern applies. And here's kind of the classic diagram. This is straight out of the POSIT 2 book, and it looks a little daunting at first, but once you understand it, it's actually pretty easy to understand. So some client, let's call it client thread 1, makes a synchronized method invocation, like let's say it does a take call on a linked blocking queue, and that will then go in, and that take method will transparently acquire the monitor lock, which of course will be a reentrant lock for the take lock. So it'll go ahead and try to get that. It may have to block if there's somebody else who already owns it, but whenever it gets that lock and then it checks the state of the object, it'll discover perhaps that the implementation at that moment has no elements in it. There's nothing in the linked blocking queue. So in that case, rather than spinning, it's going to go ahead and block on the monitor condition. So it's going to go ahead and make an await call on the underlying not empty condition object. And that will atomically release the monitor lock and put the calling thread to sleep. So client thread 1 will be asleep. So those operations are atomic. Very important to remember that. And that atomicity comes from the fact that we're using condition object and reentrant lock, which have those semantics. Now, at some point later, another object or another thread comes by. This is going to be client thread 2, and that will call some other synchronized method. Let's say in this case, it's going to be a put method. So the idea is we're going to put something into the queue. So at that point, that thread will come in. It will go into the monitor object, and it'll see whether or not the monitor lock is held. It should not be held at that point because the other thread has released it when it went to sleep. The take thread will have released it. And so the client thread 2 will then go ahead and acquire the monitor lock. In this case, it would be the take lock. And it will then go ahead and remove the item. And then it will, it'll put the item into the queue because it's the put call. And so in that case, it'll then go ahead and call the notify method on the not empty condition to inform anybody who's waiting, and there, of course, may be nobody waiting, but in this case, there is a waiter. It says anybody who's waiting for the queue to be not empty, you can go ahead and make progress, or you may be able to make progress. So I notify you, I call signal on you. And then at that point, it goes ahead and releases the lock, goes on and does its own thing. And then client thread 1 will be awakened. It'll have a chance to try to check to see whether or not, or it'll be awakened, it'll grab the lock, which should now be available, and then it'll check to see if the queue has any elements in it. If it does, it'll take one and return. If it doesn't, it'll have to go back to sleep again. So that's basically the logic of the dynamics between the monitor object, the client threads, the monitor lock, and the monitor condition. And that was just for sort of one path through the code. Okay. So let's talk a bit about the consequences of applying this particular pattern. So what are some of the good things? One of the nice things about this is it's a very concise programming model for concurrency control, because you can share an object, in this case, the linked blocking queue, between cooperating threads by transparently aligning synchronization with method invocations on method boundaries. And for object-oriented programmers, that's really intuitive, because you know how to make method calls on objects. And now we're just kind of interposing the concept of synchronization in the context of the method boundary. So it's really straightforward to think about and reason about. So put and take, for example, are the ways in which concurrency is taking place. And we do that by making put and take synchronized methods. Again, they don't have to be the Java synchronized keywords, synchronized methods, but they're using synchronization through, say, reentrant locks. Another nice thing about this particular pattern is it helps to simplify the coordination of method execution. So the suspended methods use the monitor conditions we talked about to determine when a thread should be suspended, when a thread should be resumed, and the order in which things take place. And I think you'll remember we talked about conditions and coordination in general as making sure that threads run at the right time, in the right order, under the right circumstances or under the right conditions. So that's another nice property of this pattern. It helps to make it easy to control and coordinate that in the context of the monitor object implementation. So in this case, we have a condition object to do this, and you already know what that does. Of course, as I always like to say, not everything is unicorns and rainbows, so there are some downsides. One of the key limitations with this particular pattern is you may end up with limited scalability. So for example, if you have a monitor object implemented with a classic single monitor lock variant, then you'll have lots of contention when multiple threads go to synchronize or serialize on that monitor object, because they're all contending for that one and only lock. So if you have a single monitor lock that protects the whole thing and it doesn't differentiate between reading and writing, or doing things at one end or doing things at the other end, that can become a bottleneck. Obviously, the way around this, or one way around this, is to separate out your operations. So you might have one lock that manages threads that put stuff into the queue. You might have a different lock that manages operations that take stuff from the queue, and so on. And you could also have differential locks with reader-writer access as well if you wanted to. And we'll take a look at the implementation in just a bit that shows how to do this for Java's linked blocking queue. So you can actually see that two locking monitor lock variant shown up in actual practice. Another potential downside is complicated extensibility semantics. And the reason for this is there's a fairly tight coupling between the monitor object's functionality and the concurrency control mechanisms that are baked into it. And so that can get a little bit tricky if you're not careful. For example, you can see here that this code, this is the code we'll look at later from linked blocking queue. It kind of tightly couples the logic, which for things like enqueuing and dequeuing and so on. And it's very tightly coupled with the coordination of the concurrency. So you've got, awaiting and signaling and doing things that are going to notify and notify all and all this kind of good stuff. And there's actually something that talks about this called the inheritance anomaly problem, which is a good academic issue that came up many years ago, probably 20, 25 years ago. You can read about it at this link. But the basic problem here is we're kind of tightly coupling stuff so that if something changes, you have to go through and perform very precise surgery to make sure your changes don't break stuff. Before we wrap up our overview of monitor objects, let's talk a little bit about some places where they're used. They're very widely used. They get used in lots of interesting places. One kind of classic example, really, where this all came from were the so-called Edsger Dijkstra and Tony Hoare style monitors. This goes back probably to the late 60s, maybe early 70s, where they describe the use of monitors and guarded suspension and monitor objects and so on. And they were talking primarily in terms of programming language features that would encapsulate functions and their internal variables into thread-safe modules. So if you read the monitor site at Wikipedia, the monitor page at Wikipedia, you'll you'll learn about this pattern, and it goes way back to the dawn of concurrency in computing back in the early days. And there's lots of cool variants of that described in that link. We, of course, have seen Java objects with synchronized methods and blocks. So this is actually captured in the Wikipedia page on the monitor objects in terms of something called implicit condition variable monitors, which is what you get with the built-in Java monitor objects. And then if you want to go further, you have to use the reentrant locks and condition objects in some other way. Any Java object can be used as a monitor object. And that's been true since day one, back to the days of Oak, probably. Oak was the earlier version of Java. There was a predecessor that came out of a project in Sun, which was developing some really cool, way ahead of its time tablets that are interesting to take a look at. If you ever want to learn about the early days of Java, take a look at something called the Star 7. And it was a very interesting platform that James Gosling and his colleagues defined. I should also mention briefly that because of the fact that Java objects are monitor objects, they carry around a fair amount of heft with them. They have to have a monitor lock, they have to have a monitor condition and another state. And so for that reason, in recent versions of Java, I believe starting in Java 14, which came out maybe a year or so ago, 2 years ago, they introduced something called records. And records are plain old Java objects. They're just pods, data structures. They only hold fields and state. They don't have all the other trappings of a Java object. And I just started playing with those recently, and they're really fun to play with. And certain things are greatly simplified and kind of optimized by using records instead of objects. Java's built-in monitor objects are convenient for simple use cases, as we've talked about many times in the monitor object discussion. There are surprisingly few synchronized methods and blocks in Java util concurrent. And perhaps if you think about it for a second, you'd realize why there are not many, because the whole point was to define a more flexible capability in terms of reentrant locks and in terms of the condition objects. But despite the fact that synchronized keywords are not used in very many places, the monitor object pattern is applied all over the place. And a good example is the LinkedBlockQueue that we're going to talk about in more detail. You can also find these implementations in other languages and other libraries. So C++ defines a whole pile of support for building monitor objects. My ACE toolkit, which I designed quite a long time ago, probably 30 plus years ago, has all these things in great quantity. And then starting with C++ 11 and of course continuing on, they've also baked in concepts like mutexes and conditions and so on, condition variables, into the libraries for C++ as well. So you can implement monitor objects in all kinds of languages. It's not at all limited just to Java. So to wrap up the discussion of part one of the monitor object pattern, concurrent software often contains multiple threads that requires sharing of objects whose methods are invoked in different ways by those multiple threads. That's a very common design technique. And if you want to protect the state of the objects to make sure it's not corrupted and ensure that mutable shared state is not going to be incurring race conditions and so on, then you can synchronize them using synchronized keywords or monitor or reentrant locks and so on. And you would really like to be able to simplify the programming so you don't have to explicitly write low-level code. You can just make method calls, so you don't have to think about it very hard. Monitor object pattern makes it possible to do that because you can have the same basic programming interface by making method calls, be it in one thread or multiple threads. You can also coordinate the execution sequences by using those conditions we talked about. And so that's basically the summary overview of monitor object. And what we're going to do now is we're going to take a look in more detail at the implementation of the monitor object pattern in the context of the Java LinkedBlockQueue class.